Later. So it's a pleasure to have all of you today for a really exciting lineup, thinking about generative AI and how that can be used for weather to climate timescales to improve the modeling of that, how we can actually ingest data in the pipeline at scale. And so we are going to be talking about the ocean. We are going to be talking about the atmosphere. We are going to be talking about data interfacing and interaction, how those tools can be really transformative in many aspects of in terms of the type of work we are doing. And we are going to get started with Lorzana. She's professor at NYU. She's been leading a big initiative called M Squared Lines, where they were some of the first ones, or the first ones, I would even say, looking at how we could use AI to improve climate modeling and especially ocean modeling in that regard. So very much looking forward to your talk. Thank you.
All right, good morning, everybody. Pleasure to be here, as always. So as Pierre mentioned, I'm Lorzana, I'm faculty at NYU. I'm also a LEAP Geoscience Director. So it's always great to be here and actually talking to the community at large. So what I'm going to talk to you about a little bit is how we've been using AI to improve climate simulations overall. So hopefully I'm going to try not to have too much jargon, but just try to give you a little bit of an overview of the type of ideas we've been kind of trying to push forward. And so nothing better than to start with, a few animations. So those are sea surface temperature coming out of a climate model. So the simulations come from the GFDL lab, not too far from here in Princeton. And it actually represents really the full Earth system model. So we're actually kind of modeling the ocean, the atmosphere, the sea ice. They all interact with one another. And the simulations that you see are along the Antarctic Peninsula. So let me try to play it again. Because movies are great. And so we're looking at sea surface temperature. Good. Okay, great. Sea surface temperature along the Antarctic Peninsula in those three simulations that are run at three different horizontal resolution, meaning that the grid box size of the model is basically different in those three simulations. On the left, you have something that has basically an horizontal side of about 100 kilometer by 100 kilometer. And you can see it looks a little bit viscous. It looks like peanut butter compared to when you increase the grid box size, which are finer and finer. And that means you can actually resolve a lot of the finer scale and a lot of the turbulence that is important for the ocean. Now, of course, as you increase resolution, you increase computational cost. And so it becomes a lot more expensive computationally and a lot less efficient to run at high resolution for very long time scales or have large ensemble if you want to actually explore extremes. So that's been one of the bottlenecks, I would say, in climate simulation and oceans in particular, where we have a very wide range of scales that interact continuously with one another. So if we think about the challenges in ocean modeling, and we always say a challenge is an opportunity, and where opportunities with AI come about. So one of them, as I mentioned, computational costs limit the resolution of existing climate simulations, right? And that's true for the ocean, the atmosphere, the ice. And so that leads to missing pieces of the physics. For the ocean, it's going to be turbulent processes, but we know they're important because they actually influence the large-scale ocean currents, right? So the Gulf Stream that actually transport warm water from low latitude to high latitude has basically a large influence on, climate around the world. So, missing that physics is actually an important part of, having, you could say, uncertain or inaccurate climate simulations overall. And so one thing that we can do is to use AI to actually capture this missing physics and try to improve climate models without, again, the additional computational cost of increasing the resolutions of the model. Another avenue that has been extremely popular, and I'm sure you're going to hear about it today, is trying to fully basically emulate or machine learn the entire trajectory of the climate system. So we have a lot of beautiful AI for weather, models out there. You're probably going to hear about ForecastNet from NVIDIA, GenCast. So they do a fantastic job at fully machine learning and replacing the, numerical simulations that we're used to. But they quite often become unstable because they start accumulating some noise. So at certain point, the simulation becomes a little bit inaccurate in some ways. And AI and diffusion model can actually help kind of, tame those instabilities. They actually can help, if you want, bring those trajectory back to where they belong in some ways. And I'll show you an example of that. The third one is trying to actually bridge the gap between observations and simulations. And so again, try to take those, AI full emulators in their kind of stochastic way, meaning I can generate a lot of ensemble and being able to actually ingest data to actually try to improve the representation of different tracers in the ocean. And I'll show you an example of that for biogeochemical tracers in the ocean. So trying to accelerate this idea of using diffusion model and GenAI to kind of basically, if you want, slowly build a data assimilation system, or at least a representation of biogeochemical tracers in the ocean. Okay, so I told you what I'm going to talk about. Now I'm just going to show you just a few plots just to exemplify what I'm saying. So if you take a high resolution simulation and kind of, take a little snapshot of it, this is what turbulence in the ocean would look like. It will be the same in the atmosphere. Actually, you're going to have a lot of, lot of wiggles. They're quite important. They're very energetic. They actually basically drive some of the ocean currents. But if you run the same model at lower resolution, so where the grid box size of your model is actually coarser, then you have less turbulence, and usually your currents are less strong. And again, it will impact the long-term climate. So what we've been doing is to actually learn the distribution of this missing physics to implement in the low resolution model, and trying to capture that by being faithful to the physics, meaning that's where GenAI comes about. It learns a distribution given an input. And so we'll learn the distribution of the missing physics given the input of the coarse resolution model. And then we can implement that into the simulations. And so here is our attempt to implement that in an idealized simulation where now, without increasing the computational cost, we actually capture faithfully the turbulence in the ocean, and then overall actually improve the large-scale transport of tracers and other aspects of the system. So again, this is a way to use AI to learn the missing physics from data directly in a way that remains faithful, again, to the physics of the oceans, and to directly improve simulation without additional computational costs, because you learn this kind of missing physics only once, and you can implement that in your model. The other example, as I mentioned, is, well, we're trying to move away from kind of the traditional solving equation on a grid, right? And can you actually learn the evolution of the system directly from data if you add the simulation output? So there, it's a lot more efficient, because usually when you actually machine learn the full evolution of the trajectories, you actually 100 or 1,000 times faster than the original traditional model that you would have. So you can already imagine what you could do, right? And you basically can run a simulation of weather or climate, on a single GPU on your laptop. And that's really kind of where we're at right now. Some of the big tech can do that in an amazing way, right? And again, we're going to see some example today. But one thing that they suffer, and is what this movie was showing, which is up here, we would have a traditional simulation of turbulence, again, for the ocean or climate. Down here, you would have an AI emulator that tries to actually mimic that at a much faster pace. But then slowly, you can see almost like you see on your, in the old TVs, for those of us who are old enough to remember that, then you're going to get a lot of statics and a lot of noise, right? And basically because those emulations kind of accumulate error over time, and they become unstable. Now, one thing that GenAI can do is really kind of this beautiful idea, which is kind of, if you want, remove the noise of those simulations and kind of bring them back to their original trajectory. And it can do that in a very efficient way by kind of, capturing the underlying property of the dynamical system itself. So this is something that we've implemented, and we call it the thermalizer. So we're trying to thermalize the trajectories that are, trying to go out of range. The traditional numerical model is on top. The middle one will be a traditional AI emulator that auto-regressively trying to simulate the trajectory. It becomes unstable. And the one below would be the AI emulator with this kind of thermalizing effect. So using diffusion model, if you want to denoise the trajectories and making them actually more akin the original simulation itself, capturing the physics. So here we really are kind of bridging the gap between physics and diffusion model and GenAI to improve, I would say, AI-driven models. So that was our second example. The third one is, that's great. Here we're relying on simulations for which the flow field is something that we understand, and we try to accelerate in some ways and make it more faithful. But one of the holy grail usually is also being able to actually ingest observations. So now both simulations and observations are uncertain. And so now we need to take that into account. And the way to take that into account is to, if you want, embrace uncertainty. And so those diffusion models, or the generative AI type models, what they have is they actually learn a distribution. So they learn basically the possibilities of what the trajectories could be. And by taking that into account, we can also see if it fits within the observation and then ingest the observations with their own errors. And so we're doing that basically by trying to, what we say, close the gaps between the evolution, the coevolution of temperature, oxygen, and carbon in the ocean. So basically how those type of tracers evolve in the ocean over time. We know it's important. It's important for, our planet overall, how much heat, carbon, oxygen is being taken up. The ocean is very much kind of the lungs of the climate system. It breathes in and out those tracers, and they will influence climate, again, on a wide range of timescales. So what we've been trying to build is kind of building, if you want, the backbone of this idea of bringing observations and models together by using, again, generative AI and those diffusion models overall that will actually both accelerate the simulations, but also ingest the uncertainty in the different trajectories of the world, if you want, that we actually see today with the uncertain observation. So here is basically work done with colleagues at Chicago and Princeton, trying to actually, again, represent biogeochemical tracers in, if you want, a distribution manner by using a stochastic emulator, so a diffusion model. And here, what you see here are the probability distribution of temperature and carbon in those simulations and a different type of distribution. I'm not going to explain everything. All I want you to kind of look at, if you want, are the tails of the distribution, where those kind of generative AI models are usually more faithful to the extreme values than the traditional emulators or the numerical models themselves. Because again, they can capture a wide range of possible states of the ocean over time. So it's kind of a worldwide view of the type of things one can do with generative AI overall. Improve simulation, accelerate them, and bridge the gap between models and observations over time. And that's really kind of opened the door to a lot of new ideas. And, you can learn more if you want from, the M Squared Line website, where we have a full team of people working on those ideas, and happy to talk more during the panel. Thank you very much.
Thank you. Thank you, Laura, so much for that great talk. Next, we will welcome our next speaker, Francesco Emorlano.
Yeah, thanks, Molly. Good morning, everyone. My name is Francesco Imorlano, and I'm a postdoc researcher at UC Irvine and the Lip Center. It's a pleasure for me to be here today, and let me thank Lip Center for organizing this panel and for inviting me today to give an overview of how GenAI can help with climate projections. As we know, over the past decades, human activity has caused a rise in atmospheric CO2 and other greenhouse gases that reached levels that we've never seen before. And this translated into an increase in temperatures on a global scale, with the latest report from the Copernicus Climate Change Service that reveals that 2024 was the warmest year on record since the pre-industrial period. Such abrupt changes in the climate system are making extreme weather events more frequent and intense, with huge damage and loss of lives. And we already count a lot of examples in 2025 in many regions around the world. So I think we all can see why there's an urgent need for authorities and policymakers to take proper actions. We can divide actions on climate change into adaptation and mitigation. And for society to adapt, what we need is predictions of future climate variability and change. In many cases, this information is required mainly for local areas, and the time horizon goes from years to decades. In contrast, for mitigation, it often involves questions on longer timescales, like at what level we need to stabilize CO2 to avoid dangerous climate change. But anyway, we can understand that when it comes to climate, what we want to predict is how it will change in the next decades and centuries according to anthropogenic and natural forcings. Global climate models are the tools that now scientists use to project climate change. These models are numerical representations of the climate system that implement and run the fundamental laws of physics on supercomputers. They simulate the future climate and global warming according to the SSP-based scenarios that were introduced in CMIP6 and combine possible ways in which society might evolve in the future with the corresponding greenhouse gas emissions. However, these models still exhibit great uncertainties in their projections due to the chaotic and nonlinear nature of the climate system that leads to an unpredictable form of uncertainty called internal variability. Also, there's uncertainty related to the evolution of paths that society might take in the future, and that's the scenario uncertainty. And models are only numerical representation of the climate system, so they come with a lot of different structural choices and assumptions that lead to the model uncertainty. So we understand that climate simulations contains different levels of uncertainty, and a single model run is not enough to project the climate with its variability. That's why we need to approach climate predictions in a probabilistic way. What scientists generally do is to use ensembles where each model is run multiple times, each time with slightly perturbed initial conditions, and in this way to generate a spread of trajectories instead of a single value, since a single prediction cannot capture the range of possible futures and extreme weather events. The issue is that running these complex numerical models requires huge HPC resources and is also very time consuming. This means that it's not feasible to perform more than 50 or 100 simulations per ensemble, and that's sometimes too small to capture uncertainty and extremes in a proper way. Now, how can GenAI help with that? I think that all of us have played with online image generators at least once. We usually specify some kind of conditioning information, which can be a text or an image. This is fed to the generative model and it returns images. For instance, you can ask for a fun image about the importance of GenAI for climate projections and get some nice results. You could also use the same prompt to generate a second image and even a third one and so on. Now what we can do is to apply this kind of methodology to predict different plausible trajectories about the future climate instead of a single prediction that approximates the mean and is given by deterministic machine learning models. And the generative models, especially after the training phase, they are also more efficient and faster compared to numerical models. Thus, they allow to generate larger ensembles of climate projections. One of the most popular type of generative models are diffusion models, as also mentioned by Laure. The basic idea is that during the forward process, the model starts from an image and adds an increasing amount of Gaussian random noise until the image is completely corrupted and becomes pure noise. But what we are interested in is to go from noise back to the image, and this is the reverse diffusion process. What happens during the training is that the model learns to start from a random Gaussian noise plus conditioning information about what the results should look like, and remove this noise step by step until it gets the final result. So how do we adapt this to climate now? The first thing that we can change is the conditioning information that should help to predict temperature maps. Our data consists of daily temperature maps simulated by 9 SMIP6 models for 3 SSPs. The spatial coverage is global and we have one map per day. We also have annual global mean CO2 equivalent values simulated by a reduced complexity model for the same SSPs and the same period. What we do is to give indices about the CMIP6 model, SSP scenario, day of the year, and CO2 equivalent value as conditioning information to the diffusion model to generate the corresponding temperature map. In this way, we obtain a single emulator that can learn from multiple CMIP6 models and scenarios and then generate temperature maps for specific years and days of the year accordingly. Now let's look at some results. Here we can see the maps generated by the diffusion model where when conditioned on CSM2 SSP 370 for each day between 2070 and 2075, and the maps are then averaged over this period. We notice that the maps are pretty close to the original ones, with the largest differences in regions with complex topography and coastal areas. We also evaluated the histogram of temperatures over the same period for the locations corresponding to LA and Reykjavik. We were happy to see that the diffusion model captured the complete probability distribution, including details that are critical for the analysis of extremes. Here we analyze the temperature maps generated by the model when conditioned on EC Earth 3 for the same period and for the three SSPs, and the maps were averaged over space. The diffusion model does a pretty good job also in predicting the temperature trend over time, although we do not model any autocorrelation. Now let's look at some examples of what we can do. Let's suppose we want to know how the temperature distribution will shift according to CSM2 on a specific day between September 2015 and 2100 under a specific SSP and for two cities we are interested in. Our model allows to generate ensembles of 1000 maps for the specific conditions and draw the temperature distribution for the specific locations at the reference times. And also the generation is pretty fast when conducted on batches, so with some sort of parallelization. Or again, let's suppose that we want to evaluate what's the shift across the SSPs in the distributions of temperatures simulated by the same model on September 12 in 2100 for the same cities. Such location-specific probabilistic projections are important for things like infrastructure planning and risk assessment because they provide decision makers with a full range of possible outcomes. We may also want to analyze and quantify how CSM and PI, two different Simip6 models, differ in their projections across seasons in 2100 under SSP 585. The special patterns we see show like biases that vary seasonally with the corresponding distributions that quantify this difference in a probabilistic way for specific locations. Understanding these structural model differences helps to interpret how robust climate simulations are and identify regions where the model agreement is high and those regions where we need more attention due to a larger model divergence. Just to conclude, generative AI unlocks features that have the potential to impact climate change projections and several downstream tasks, such as scenario comparisons, assessment of extreme weather events, and planning of adaptation and mitigation strategies at regional scales. However, of course, at the moment, we can only look at these models as complementary to numerical models, since there's still a lot to do in terms of validation to be able to really trust them, especially concerning the use of these models with data that are out of distribution of the samples that were trained on. Thanks. Thank you so much.
Thanks a lot, Francesco, for the great talk. So we are going to move on with Mike Pritchard from NVIDIA, who's going to be talking about a new project that they had at NVIDIA called Climate in a Bottle. So sounds like a Jenny, but that you will see. That's related.
Thanks. Yeah, so I'm Mike. I'm here on behalf of a bunch of engineers and research scientists from NVIDIA. Don't allow. Yeah, so I'm the research director for an initiative called Earth 2. We're trying to build open source technology, including a bunch of generative AI for weather and climate science. I'll give you a little tour of that. And I'm affiliated with UC Irvine, where I was a professor for 12 years and part of the LEAP multi-institutional Science and Technology Center, which I love. So it's lovely to be here. So of course, it's important to remember physics models matter. Climate projection is going to require physics models. AI is very complementary in very interesting ways. It's very interesting to think about how they can be best used in concert. These are some of the trade-offs. At NVIDIA, we're building a bunch of different things in weather modeling, in downscaling, in high-resolution weather modeling. I'll give you a superficial tour of some of them, and then we'll dive into climate in a bottle. So one thing we're interested in is turning blurry stuff, low-resolution climate projections, which we have a lot of the future, into high-resolution stuff. Generative AI turns out to be great at that. Correlative is a model we have that does multivariate super resolution plus new channel synthesis, you can generalize things that on the high resolution that you didn't have at low resolution through correlations. And it's called correlative because it's a corrective diffusion model. We use generative AI downstream of a deterministic regression component, and that turns out to help localize the problem in important ways for scalability. When you localize the downscaling problem, then you can expand to very large domains. So here's an example of correlative turning blurry weather predictions into high resolution predictions of precipitation type, probabilistic precipitation type that we did in collaboration with the weather company. I should say that generative AI can seem scary sometimes because it seems like it's very costly to train and to inference, but please don't worry. Performance engineers have taught me that after you train a wasteful model, you can distill it into something 50 times faster. So Cordiff has enjoyed this, and if you're interested in performance optimization, check out the repo diffs that encapsulate those performance optimizations. Okay, so another thing I'm interested in is cloud resolving modeling. A big part of LEAP's focus is trying to learn from high resolution physics that we can't computationally deploy at climate scales yet. And so if AI can radically transform the way we simulate high resolution physics, that has deep implications. So it's a proving ground of this. We train a model called Stormcast, which uses the same approach as CoreDiff, sort of a first guess from a regression model, and then a denoising diffusion generative AI model downstream of that, not to do the super resolution task, but to do the mesoscale prediction task. So the evolution in time of the high resolution. And these are simulations from Stormcast ensemble members versus a SOTA physics model showing kind of weather in the United States and convective storm clustering and a proof of life there that you can quantify in the form of a score. And it turns out AI, which has already disrupted the world of macroscale global weather forecasting, I think is on the verge of disrupting the world of national microscale forecasting. We're seeing the first signals of skill comparable to physics models that we're seeing in 2022 on the global realm. Okay, but I'm here to talk about climate in a bottle. That's our latest research project. I'm really excited about it. Here's a schematic. Climate in a bottle is sort of a foundation model that tries, like a video language model can mix together informations from video feeds and text and allows you to do amazing things like talk to a self-driving car. This is sort of analogous to this. We're mixing together two types of climate model output. Observation constrained error 5 reanalysis, best estimates of the historical state, 25 kilometers, and really high resolution simulations of the planet. They come from a physics simulator, 5-kilometer resolution, high resolution, low resolution. Climate in a bottle learns them both kind of foundationally. And it's not a predictor, it's a sampler. So it's a thing that's for climate informatics. When you need to pull samples out of an archive of data that might have come from a physics model, that's an annoying task. And generative AI gives a way to be formal about our conditioning. We can condition based on climate inputs like where's the sun, how warm is the ocean, and other things, and ask generative AI to produce samples. Just like you can take an LLM and ask for a very niche type of art to be generated, and generative AI is a powerful way to hone in on a subset of the learned probability distribution that you can guide and steer. So climate in a bottle, we subjected it to a battery of climate variability tests. We confirmed that our macroscale generator in this model is able to produce important modes of variability that matter to weather and climate, like the daily cycle, the seasonal cycle. These things have different patterns and characteristics and amplitudes, and that it's able to produce subtle trends, reproduce subtle trends in climate from its conditioning, behind the noise of all that variability. So there's a bunch of diagnostics in the paper if you're interested in that kind of stuff. But then I think one of the really cool things it does is it allows you to generate and do an amazing compression. So from very low dimensional information like some numbers, time of day, time of year, and a very blurry map of the sea surface temperature, how warm is the ocean? Most of the climate change is absorbed by the ocean and the atmosphere feels it. Please generate me, that's like a few hundred kilobytes of inputs. Please generate 13 megabytes of outputs that look like this. So 4K resolution, 13 million pixel, visible imagery. And the way we made that computationally possible is with a method called patch-based multi-diffusion. So another way to take the pain out of generative AI models that are powerful like diffusion models, if you have a spatially local problem, which we believe the downscaling problem is to use this method in imagery that sort of uses overlapping patches so that you can learn a small model that can be deployed globally. We had to update that a little bit due to the nuances of how modern global cloud resolving models have decided to store their information on Helpix grids. And we have an open source library called QHelpix that has some regridding algorithms there if you could make use of them. But these are the results of climate in a bottle. So a few numbers in, out comes a high resolution map of visible light and surface temperature and outgoing long wave radiation, where the dark regions are places where deep storm clouds are blocking long wave radiation from escaping the planet, and co-located with some of these systems like this one, that's a tropical cyclone. You can see the wind field, the wind surface expression of the tropical cyclone. So that's what climate in a bottle is. It's a multimodal 5-kilometer global foundation generative model that's quite carefully conditioned. And because it's a foundational model, you can do many things with it. You can do super resolution. I've shown some of that. But you can also share information between the modalities, infill channels that do exist in the simulation but don't exist in the Era 5 data. And please check out the paper if you're interested in that. I'll tell you about one feature that I think is pretty cool because I've never seen it before. So often a stakeholder comes to climate model data and it's really hard to find what they want. You know, you've got petabytes of output, but you care about your region and you care about tropical cyclones. And sifting through that haystack to find that one tropical cyclone you care about over your region is a huge, laborious, high latency data analytics task. And so wouldn't it be nice if, like we can in images, we can just ask for things directly with coarse outlines and have powerful diffusion models fill in the details while respecting the training data's manifold? You know, wouldn't it be nice to be able to have climate informatics systems where we ask for hurricanes directly, maybe in a text modality, and receive satisfying output that's faithful to the physics simulation it was trained on? So this was what led us to ask if we could add classifier guidance to query climate in a bottle. We trained a tropical cyclone classifier alongside the macro scale generator, and it kind of works. Now you can pass in one more input, which is a heat map of where you'd like to see tropical cyclones, and the model will return global states that match that conditioning that have a tropical cyclone in the desired location. So I've never seen anything like this in the world of climate informatics. I'm really excited about what it might mean for the future of interactivity and being able to do what-if scenarios with output that we've normally had to navigate using technical personnel and laborious high latency analytics. So I'll leave it there, but I want to remind you there's a bunch of tools that you can make use of, that many of which use generative AI. Our mission is open source. Earth-2 Studio is a great place to find all these tools. We're not trying to serve weather products at NVIDIA, but we are trying to accelerate the ecosystem. It's a great use of GPUs. We want to make sure you have an excellent experience on our GPUs if you, and this tooling is there to facilitate that. So yeah, please talk to me if you'd like to hear about more details or come to our conference in October. Thanks.
Thanks a lot, Mike, for the exciting results. Then we are going to move on to Gideon Dresner, who's going to be talking about what we call data assimilation. So how do you bring together data and models, especially for weather forecasting? You know, so that's something we are doing on a routine basis, and how we can accelerate that using AI. Thank you.
Hi, everybody. Can you hear me? It's good. Yeah, I'm presenting work on behalf of Brightband. We're a new startup. It's existed for a year and 2 weeks or something like that. And I'm really excited to present some of our sort of preliminary work on a slightly different problem. So on, generally speaking, on weather forecasting, so not climate per se, and specifically on data assimilation. And I'll explain exactly what I mean as I go through this. This is really the work of all of Brightband, but I just want to highlight some of my colleagues, Drew, Ryan, Alex, Hans, and Daniel, who've made huge contributions to all of this work. Yeah, a little bit about Brightband. Like I said, we're a new startup company. We are a public benefit corporation. Happy to explain that in questions if you'd like to discuss. And I would say that generally, you know, we're trying to, we're one of the many groups like NVIDIA and others that are trying to bring the AI for weather, AI for climate revolution to the people. And to that end, you know, we're building an end-to-end probabilistic forecasting system. That's sort of what I'll be presenting mostly on today. We're open sourcing benchmark data sets, and really excited to sort of give you a flash of what we've got there. And we're also providing you know, general tools and evaluation frameworks. So a big part of our work right now is focusing on observations. And we're focusing on observations because we believe that this is the future of AI weather. Sort of very broadly speaking, you know, you have observational data, this sort of heterogeneous, you know, data set from many different sensors. You want to create an atmospheric state from that. And you want to take that atmospheric state and feed it into a forecasting model, which is going to auto-regressively roll that out and give you predictions. And traditionally, or until now, with the the great revolution in numerical weather prediction, we were able to use partial differential equations and very broadly speaking, physics to do both, both of these steps. So the data assimilation step, which goes from observations to atmospheric state, and then the forecasting step, which is unrolling that forward in time. And what we've seen in the last 2 to 3 years is AI, ML, kind of computer science-ifying or AI-ifying this forecasting step. But the data assimilation step, which ironically is the most machine learning-esque of the system because it is going from observations to a kind of latent atmospheric state, which is unobserved, is still being done in so-called traditional ways. So it's natural for us to want to tackle this problem, and there's good reason for it. It's not an easy problem, which we knew going in, and we're discovering how complex it truly is. But that's sort of our big bet, and that's what we're working on. So that gave rise to the unexciting, but I think very elegant name of our work, which is ADA. So that's the AI data assimilation method. And I'll explain sort of on a high level what the goal is. We want to do global data assimilation right now. So that means, on a quarter-degree grid globally. We want to estimate atmospheric states from level 1 observations. So level 1 observations are just very raw observations. They're practically exactly what sensors in space or sorry, what I mean is from satellites or from weather balloons or ground stations. Just what is the sensor reading off from the planet. And we're going to use that atmospheric state that we've inferred from the level 1 observations to initialize a AI forecast model with our goal of getting as close as we possibly can to the European IFS model. And we have this running operationally, which means that it's running right now every 4 times a day on the synoptic schedule. So I'm not going to go as much into the technical detail as some of the other talks, but I do want to give you sort of a high-level sense of what we're doing. I think sort of like the climate in a bottle work, we're taking heavy inspiration from the state-of-the-art in machine learning, AI, computer vision, and our sort of belief is that there may need to be some small modifications to this technology, but that by and large, we're going to take it out of the box and we're going to apply it to this problem, and it's going to work very well. So the Natten transformer, this is a neighborhood attention transformer. It's a general computer vision approach, maybe the best, maybe state of the art, one of the latest for sure, but you could probably try other ones, and I don't have a super biased perspective other than this seems to be doing really well right now. So what did we put in this transformer? Well, we took the observations, which I sort of hinted on. You'll see a bigger image of these observations in a minute, but right now I hope you can see that there's these kind of sort of striations, and those are literally where a satellite has been passing over the Earth. So we take those observations, which are not on a uniform grid around the Earth, and we grid them. We sort of snapped into the nearest grid point. And then we take the previous forecast. So if you're familiar with this area, that's often called the background state. And morally, the interesting thing is that if you want to know what the current atmospheric state, the forecast from 6 hours ago is a pretty good place to start. So what we do is we take the forecast from 6 hours ago, we use that and say, okay, well, this is where we're going to start off, and we're going to correct that with the latest observations that have come in. So we take those, we pass this through the transformer, we get what's called an increment, which we're just going to add sort of a correction to the forecast from 6 hours ago. And what's exciting about this sort of general design is that we can ensemblify it. So by adding noise into the actual architecture, I can fill in some more details there if you like. we're actually able to get an ensemble of increments, and that's going to give us some estimate of uncertainty estimate. So basically, we have a button that we can press, and we can get 10, 20, 50, however many increments we need to get some sense of that probability distribution. What did we actually train this model on? Well, I'm really excited that we trained it on a data set that we've constructed and released for everyone to use. And we represent that this release with the version 1.0. So super excited about this. This is the Ninja AI data set. Ninja is sort of this joint collaboration between NOAA and NASA, which is an archive of level 1, very raw observational data. It's been kind of, I don't want to say locked up, but it's been in data formats that are very convenient for people working in government, but maybe not so convenient for people working in research or in AI or in cloud compute and so on. So we took all those files and we processed them to get about 50 terabytes of curated, cleaned up observations. They're in cloud native AI ready format. We released a small Python library you can use to just install, and just to give some sense of, each row here is a completely different sensor from different satellite observation or, geospatial, or just a very heterogeneous set of observations and ever growing. And for those of you who are programming these days, jot this down, because you can install the Ninja AI library right now from pip. And you could run this and generate this plot on your laptop right here. So if you have had any exposure to what raw observational data looks like, this is incredibly short and sweet. So we're really excited about that, and we're sort of hoping that this might push the community towards a kind of Era 5 moment in AI ML for weather research. Okay, so I'm not going to go too deeply into details on results, but I just want to give you sort of a flash of some of the stuff that's been coming out of this work. Here are some wind maps, so vertical and horizontal winds. And this is from our ensemble method. And we're just showing here that the variation in that ensemble is matching the variation from the ensemble method from the European forecasting system. So we're sort of, we're not capturing all the variability, but we're roughly, we're going in the right direction. And as I promised, we can take that initial state that we're generating and run it through an AI forecasting system. We chose AIFS from the ECMWF, but you could choose a different one. And we're able to, via hooking these pipes together, get an end-to-end from observational data all the way through to a forecast system. And when we do that, the numbers are going, again, in the right direction. I wouldn't read too much into each one of these values, but yeah, the takeaway here is that we're doing something right, and we're sort of pushing this forward. And yeah, again, as I promised, Ada is running operationally. So we're running it every day on the synoptic time schedule. It's 4 times a day, every 6 hours. We're generating forecasts from this AIFS single, which just gives a single deterministic forecast, and AIFS ENS, which is the ensemble forecast. We've managed to make this operational using not open source, but publicly available tools called Daxter and Modal. So if you're on the operations side, that might be interesting to you. It's been a very smooth process getting that operational. And for those of you maybe more on the business side or who really know IFS very well, we're able to give a full forecast an hour before not just the IFS forecast, but the pre-scheduled IFS. So that's pretty early. Quick summary: level 1 observations to global atmospheric state. We're taking that global atmospheric state, fitting into a forecast model, and it's running operationally. Would love to talk. Find me here, send me an email. Thank you.
Thanks so much, Gideon. Really exciting stuff. So we have two speakers coming up next. So we're going to be moving with Ignacio Lopez Gomez from Google, who's going to be online and talking about downscaling. So something that Mike mentioned, how could you make accurate description about the climate system or the weather at a local scale when you just have global information or very regional information? Ignacio, if you can hear us.
Yeah, I can. Can you hear me?
Yeah, perfect. Thank you so much.
Perfect. Okay. Can you see my screen as well?
Yes.
Okay. So yes, as Pierre mentioned, I'm Ignacio. I'm a research scientist at Google Research, and today I'm going to be talking about how we can use generative AI methods for downscaling climate projections in a cost-effective way. And what this cost effectiveness is going to enable us to do is to really apply this technology at scale to large ensembles of climate projections, which is important if we want to get actionable climate insights at decision relevant scales. So the reason why we're interested in this problem, in downscaling, is due to the fact that current climate projections are too coarse to capture some of the physical processes that affect local climate. Now, to put this into perspective, we can consider the question of what is the extreme precipitation risk in the big island of Hawaii, or what is going to be the extreme precipitation risk in the island in the future. Now, the problem when answering this question with current climate models is that the entire island of Hawaii actually fits into a single grid cell in most of the climate models that are available today. And so at best, the answer that we would get from these climate models would just be an average risk over the island. Now, in reality, extreme precipitation risk and many other factors can vary very strongly from the eastern to the western side of the island. And so just having access to an average value for the risk is not going to be very meaningful for this application. And so if we want to really harness the power and the information that is given to us by current climate projections, we do need some methods that can bridge the gap between the resolution of those projections and the scales that we need in order to make decisions for downstream uses. So one methodology that has been used to produce this high resolution climate information is a process known as dynamical downscaling. So this process essentially uses a regional physics-based model to essentially simulate climate at high resolution over a limited area domain of the world. So these are methods that are still physics-based, but they're going to trade spatial extent for spatial resolution. And they are driven by the boundary conditions and the large-scale forcing of the climate model that we're using as input. Now, this approach is very appealing because it's still based on the physical equations of motion, and therefore we believe that it's capturing how many of the fine-scale physics are affecting local climate, and so they can give us robust estimates of what's happening at the smaller scales. The problem with this approach is that because it's still physics-based, it's still too expensive to apply to large ensembles of climate projections, which is the typical application that we're interested in if we want to, for instance, understand what's going to be the risk of low likelihood extremes in the future. And so we need to find cheaper alternatives to do this, to get this kind of information. Now, traditionally, there have been cheaper methods that have been developed for this specific task, and they're typically grouped in what's called statistical downscaling methods. These methods are usually designed to preserve trends and in climate projections, and then just add fine-scale details based on historical observations of climate. Now, although these methods are cheap, they typically have some limitations because their simplicity makes them unable to capture some correlations, maybe across variables, space, or time, and this can limit their value and lead to underestimation of certain risks. And so an example of this, to see an example of this, we can consider a system that is trying to downscale the two components of horizontal wind over some area of the world. And here I'm considering just California and a part of the Western US. And so if we have a system that is downscaling the two components of the wind separately without taking into account the potentially positive correlation between the two components, there will be some locations in the world where these components are actually positively correlated. And this is going to lead to an augmentation of the risk of extremes in, for instance, the wind speed. And so what happens if we neglect these positive correlations is that in those regions, we're actually going to underestimate risk. And so this is something that we can see here in the example of the slide when we compare the results for the top percentile of wind speed from dynamical downscaling and statistical downscaling. We can see that there are in some locations where we are severely going to underestimate risk. And so in this context, where we propose to use generative AI methods, as well as many other groups, and we've also seen from NVIDIA that this is useful as essentially as an alternative to both the cheap but limited somewhat traditional statistical downscaling methods, as well as the more skillful but computationally complex dynamical downscaling, which is still based on physics-based models. And in particular, we propose to use here generative diffusion models, which are the models that power the state-of-the-art video generation tools that many of you might be familiar with, because these methods are excel at capturing really the rich structure of high-dimensional distributions. And this is something that we absolutely need if we want to capture the structure of climate data at finer scales. But importantly, even though these models can really capture the rich structure of climate data, they can do this at a fraction of the cost of physics-based models, as Laura mentioned at the beginning of this panel. And so we can really take advantage of this reduced cost to essentially use these methods at scale and downscale very large ensembles of climate projections and reliably estimate climate risk. And so if we actually look at the application that we're interested in and where we would want to use these methods, which is estimating the risks of climate extremes, we've actually observed in our results that these methods work really well at capturing many of the properties of extremes that are important for climate. And so here on the top panel, I'm showing one of these properties, which is the ability to capture the codependence of extremes in different variables in the climate system. And so here I'm showing an example for the capturing of the codependence of wind extremes in both of the horizontal directions across the Western US. And we can see that generative diffusion is able to really capture the spatial structure of this dependence very well, similarly to dynamical downscaling. Whereas simpler statistical downscaling methods typically fail at capturing the fine scale correlations and just essentially capture the correlations that were already given by the input climate models. Now, capturing these dependencies becomes really important in certain downstream tasks. And one of these tasks is, for instance, the estimation of wildfire risk. So wildfire risk in many regions, and in particular in Southern California, is typically a function of the combination of factors given by high wind speeds, low humidity, and also very high near surface temperatures. And so for this particular case, if we have methods that can actually capture the codependency and correlation of these extremes in different variables, we're going to be able to really get a good estimate of the risk. And so here on the bottom panel of the slide, I'm showing an example of a downscaled Santa Ana wind event over Southern California for climate projections of the end of the century. And we can see that generative diffusion models are able to really replicate the magnitude of the wildfire risk that we observe from physics-based models, whereas statistical downscaling approaches that may not be able to capture all the correlations and dependencies between the different extremes can really severely underestimate the risk. And so this is very important for us, because many downstream users may not be familiar with the limitations of the methods, and they may just take this risk at face value from different methods. And if we give them a result that has underestimated risk, this can lead to problems in the future. So another useful property of diffusion models for climate downscaling is their ability to really capture and model in a consistent and coherent way time evolving features in the system they model. And so as an example here, I'm looking at tropical cyclones, and this is a very important task in climate downscaling, because current climate models at their coarse resolution actually cannot really capture well tropical cyclones, hurricanes, and so on. And so if we want to capture how these tropical cyclones or features are going to change in the future, we cannot really use climate model output directly. On the other hand, if we combine climate model output with some of the generative AI methods that some and we are proposing at Google, we can essentially get a better picture of how tropical cyclones behave and how they might change their behavior in the future. So we're able to generate with these generative AI methods essentially hurricane and tropical cyclone trajectories that are consistent with the large-scale conditions from the input climate models. And so we can also track how these tropical cyclones are going to change with changing conditions in the future. And importantly here, we not only get with these generative methods cyclones that just look realistic, but we can actually analyze these tropical cyclones against observations. And indeed, what we observe from some of our experiments at Google is that these methods can actually capture well both the frequency and the intensity distribution of these phenomena, which is important for climate risk analysis. And so with these examples, I hope I've convinced you that generative AI methods are already revolutionizing the field of climate downscaling. And they are doing this thanks to their inherent ability to really capture complex correlations in high-dimensional distributions, such as climate data. And what this enables them to do, for instance, is capturing the emergence and evolution of tropical cyclones, or the risk of very complex compound events, unlike traditional statistical downscaling methods. And importantly, they can do this at a fraction of the cost of the best tools that we have available within our toolkit if we don't use generative AI. And so what this is going to enable us to do is to really use these techniques on very large ensembles. So for instance, we could apply this to ensembles of hundreds of members of climate projections. And we can start asking questions about what are the changes in the risk of very low likelihood extremes, such as, for instance, hurricane landfalls over the east coast of the United States. With that, yeah, I'll take any questions during the panel Q&A. Thank you.
Thanks so much, Ignacio, for the exciting results. And so we're going to finish up with our very own Professor Tian Zheng, who's going to be talking about the new kids on the block, which are agentic AI. So you might have heard about that, how you can have agents that can actually collaborate and work together to actually get an answer for you. Thanks so much.
Okay, so very excited to be here and to present our recent work on agentic AI for climate data science. And this is our team from LEAP, and we're also in collaboration with AWS to make this possible. And in particular, because this is an event jointly with Columbia Engineering, and I'm very proud to share that this work was, driven by two very bright students from Columbia Engineering School. So the motivation for this work is that we know climate information, high quality climate information is needed everywhere. People from public health, agriculture, energy, urban planning, disaster responses, all these sectors are looking for usable climate information. And I think by looking at the room, we can tell that, yeah, that this is definitely the case. And also at the same time that we know the scale of climate data today is exploding, right? So just to give you a few numbers that you can look at, like a subset of data generated by the National Center of Atmospheric Research put on AWS Open Data Platform is 500 terabytes by itself. It's only a small subset. And NASA and NOAA producing petabytes worth of data, and then terabyte worth of data every day. And then all the local agencies are collecting data. For example, New York City have hundreds of sensors across the city collecting hourly data on flooding, and all this data are out there. And on the same time that we all experience the bottlenecks in climate data science, when you can find when you read something that you could potentially use, just like all the wonderful talk you have heard in today's session, and you wonder, how can I make this to work for the question I have? So that is the motivation for our research, is how can we resolve this bottleneck leveraging today's technology? So since summer 2024, about a little bit more than a year ago, that agentic AI has become one of the hottest topic in the tech industry. So they suddenly realized that we don't have to ask a large language model like ChatGPT to give us answer from end to end. We can actually ask ChatGPT to break it down to small tasks and have a multiple large language model generative AI created tools to solve the problem in pieces and then bring them together into a bigger solution. So this is one of review paper, and one of the most popular talk I have been attending to this summer features that a virtual lab with AI PI, AI research assistant, AI PhD student are collaborating together to reason potential solutions for a hard problem. And then this is another example from statistics that we have realized that it is possible to run statistical modeling and data analysis using a chat interface. So most famously is that if you search the Moore's law to Huang's law in Google, the Moore's law basically predict that the computational capacity of today's technology will doubles every year. But that law is slowing down, so there is a lot of discussion of whether that law is dead or is slowing down. You know, we're not going to see a major breakthrough in Silicon Valley to give us the next generation of GPUs, and which led to the idea of Huang's law. Jason Huang from NVIDIA says that the current technology is not about how fast GPU computes, it's how smart the computational solution is, like whether we can leverage today's technology in smartly designed workflow to solve complex problems. So this motivates our climate data science. We're trying to create an agentic AI system for climate data science, and we're collaborating with AWS since summer 2024, and we want to unsolve the bottleneck for climate data science, in particular data retrieval, organization, automation, and reproducibility. So the idea is very simple, is that we believe there are a lot of agentic AI tools out there. You just heard tons of them. I was very busy slacking with my team with all the wonderful models and tools that you just heard. And I said, this is the kind of thing we need to integrate with the system. So there are these AI agents that can be powered by existing AI services. So these agents are a conversational agent that can take the tool and translate to natural language for the user to use. And then, but we all worry about generative AI's hallucination. So if you ask ChatGPT to give you a risk prediction for New York City in the next 20 years, and they can give you a beautiful figure, and how much you can believe in that, it depends on your comfort level with generative AI. So our vision is that we need to create a rigorous grounding for the generative AI workflow, leveraging existing research publication knowledge that humans have accumulated along with all this terabyte and petabyte data, a human-generated curation of those data sets. So this 20-page paper that will come live on archive tonight. Unfortunately, we only finished last night. We'll explain the approach we use to generate this knowledge graph. With this knowledge graph, we work with AWS to create several agents as a proof of concept that for discovery, acquisition, and analytics. And with a verification agent, will review the work of the agent to serve a second review. And then this is in there. The knowledge graph was the primary research we did. We analyzed the data structure, the description of the data set to generate the clustering of the terminologies and entities. And then with that, we were able to leverage the Bedrock large language model in AWS and a Neptune analytics that can help us navigate the knowledge graph. And with that, the one of the proof concept that is that we take one paper, for example, this New York City climate risk information 2022, and then we look at this figure and we use natural language to describe the purpose of this figure to the generative AI workflow, and we were able to reproduce this, and then even the AI even were able to compute the slope with the same return the same slope with higher precision. But you can say, okay, ChatGPT can do that, but we also create data access files for the user, which API calls, and also the raw data for the user to download, and the user can interact with further, and then in a fully transparent way. So we are very happy with this work so far, but there's still a lot of possibilities. We want to continue with the verification effort and scaling, including more tools, just like all those things, wonderful things you've heard so far, and then expanding. And we are going to leverage the vast community of scientists, hackers, students' energy to expand the development of this work, and then to resolve the bottleneck, to attack this bottleneck, but to leverage these opportunities. Thank you.
Thank you so much, Tian. One more round of applause for our amazing speakers, who will be coming back up after lunch. So please don't go anywhere after you finish lunch. But we just wanted to share a few quick announcements. I'm Molly Lopez, the Managing Director for LEAP.
Hi, everyone. My name is Catherine Cha. I'm the Senior Manager of Communications and Knowledge Transfer for LEAP.
So we will break for lunch in just a few minutes. You'll go through the doors at the very back of the room, grab a lunch, and come back to enjoy it at your tables. Feel free to turn around and join the table behind you. We hope you'll stay for great conversation with the participants and the speakers. And there are drinks in the back. If you would like water, there's a fountain right over here by where you checked in with cups. So we would love to see you all back here for future LEAP events. We currently have Dr. Gentine's course, Machine Learning for Environmental Engineering, which for the first time is available on Columbia Plus. So it is available virtually at no cost. You can find the link on Columbia Plus or email one of us. Every week, we also have a LEAP lecture in climate data science, which you can also access virtually or here in person. If you come in person, we have a light lunch afterwards, so please check out the schedule on our website. And coming up next summer, which will be here before we know it, we also have summer programs for students. We have a research experience for undergraduates and a Momentum Fellowship for graduate students. These will be posted in March 2026. It's open to students from around the country. So if you know of anybody that would be interested, or if you are a student and would be interested, please check out the website or sign up for our mailing list, and you'll be notified when those projects are announced and the applications are open.
Two more quick things before you step out for lunch. If you would like to stay in touch with us, keep up to date with our accomplishments and new events and news. We have things like hackathons and journal clubs, the lectures that Molly mentioned, boot camps, all of our educational programs. We have professional development workshops. If you would like to stay in the know about those things, please go to our website, leap.columbia.edu, and there will be a subscribe button on your top right hand of the screen. And finally, our Momentum Bootcamp in Climate Data Science. The next one is coming up in January 2026. There is a QR code. We'll leave this up as you step out for lunch and enjoy lunch. So please feel free to stroll up to any of the screens and snap the QR code to get more information and to consider joining us in January.
Okay, so I hope you had a good lunch. We are gonna get back to our business for another hour, and it's a great pleasure today to have George Deodatis. He's the Vice Dean of the School of Engineering. He's also a professor in civil and environmental engineering. He's worked a lot on hazards and flood-related risk, so very connected to the things we are doing at LEAP. Actually, was here last year when we had the Climate Week here again in the hub. And then we are going to move on to the Q&A, and you could ask all of the questions that you had after this series of great talk. Yeah, thanks so much for coming here today.
Thank you, Pierre. On behalf of the School of Engineering and Applied Science, I would like to extend a warm welcome to all of you. Apologies for the weather, especially the humidity. I felt this morning as if I were in the Amazon rainforest. So thank you for having me here at the LEAP event on generative AI for climate science. And as you know, generative AI is a huge topic of interest across our school, across the entire university, but beyond the university, I mean, everywhere, everyone is talking about generative AI these days. So I realize this is the middle of the symposium, and I trust you had a very productive discussion this morning and will continue to do so this afternoon. Let me mention a few thoughts about generative AI. It clearly presents many new major opportunities, but as well as some unique challenges. And at Columbia, we have an initiative called Columbia AI, which is focused on bringing together all of our resources in AI across the university. One example, last year we launched an AI summit, and we are also piloting a Columbia-specific GenAI platform. The possibilities that GenAI opens up in the climate field specifically will be, to put it simply, transformative. And as we know, Gen AI models come with environmental consequences. We need our best experts and thinkers working together on how to accelerate progress in ways that are sustainable. With events like today's, and with people coming together from academia and industry, this collaboration is absolutely critical. Industry and academia must collaborate, and we are succeeding along these lines. We hope to develop the new ideas that will spark success. I want to assure you that Columbia is committed to the role of a convener, bringing together these different voices to advance innovation. And I would like to thank Pierre Zentin, the director of LEAP, for his pioneering vision, leadership, and scholarship, and for making today possible. And of course, all of you for your participation here today. Thank you very much and enjoy the rest of the symposium.
Thanks a lot, George. So we're going to move on to the Q&A, and thinking about thanking people, I would like to thank Molly Lopez, our managing director for the organization, and Catherine Shah, without whom none of that would be possible. They've been really planning that for a very long time, so that's why everything is working out so smoothly as usual. We barely have any issues, I think, by now. Thanks so much for all of that. Okay, we can get started. So thanks again for the fantastic talks that we got today. Any questions to begin with, or maybe to begin? So where do you see? So you really explain like how generative AI is changing the game right now, and it's moving really fast. What's your vision, for the next couple of years? Sometimes it's hard to say even to talk about years for AI. It might be months, right? But where are you thinking that we are heading to? You know, maybe we can start with you, Laure, and could move across.
Yeah, great. Okay. Oh yeah, that's okay. Yeah, it's okay. I think we're fine. We can pass it, and so it can stay in the audience. Yeah. Great. Yeah. Thanks, Pierre. So I think definitely kind of looking at the breadth of talks, right, to this morning and the use of generative AI across the board from accelerating climate simulation, generating large ensemble, improving data assimilation. Some are the biggest challenges that we've been facing for decades, right? Where we're really kind of tackling parts of the problem, so to speak, right? How to build tools that will be useful, across the board, for the community. And so I really see the beginning of generative AI. We've been showing examples, right? And the examples are already very powerful, right? But and it's been very much across the different projects. But I really see that as the beginning. So I really see it as targeting some of our biggest challenges in building tools that will be useful for the community, but then being able to actually take, what we produce for the broader audience, right? And that's again, whether it's, private sectors, whether it's, different stakeholder across the board. So now, that would be our grand vision. And I think, part of that might be collective. How to get there, I think, I'm hoping we'll continue the discussion here today. So I'll leave it here and then pass it on to my colleagues.
Yeah, so to me, I think the generative AI is a way to connect different intellectual communities, like because the power of large language model and the translational power of natural language processing allow can break the barrier, the outsider and insider. Like some of the audience would just reach out to me saying that they when they want to find data sets, they sometimes always feel like they're new to the field, they have hard time identify the data sets. But I think generative AI can actually break down all these walls. I have been at Leap for almost 5 years, and then one of my job is to bring together the data science and climate science communities. And then the first thing we want to do is to converge the vocabulary and to clarify the different jargons and different terminology. And that used to be hard 5 years ago, but now it's super easy thanks to generative AI. So going forward, we can see generative AI play a more important role beyond terminology, actually connecting tools, serve as translator between a data set that in one format, but a downstream analysis assume a different format, so that generative AI can actually fill in that gap for that workflow. That's what I think will happen in a year.
Yeah, I think, I guess at Brightband, and I also think about the field kind of in three broad categories of models, metrics, and data. And just, yeah, echoing what other people have said, the data is going to become sort of a one-click go situation where you're going to import a library, or you're going to click a link and you're going to get that data set in a way that is ML friendly. And there might be some tension with the friendliness with previous approaches, but the trend is going to be towards making data ML friendly and cloud friendly, as opposed to, HPC friendly. On the metrics side, so far we've been really focused, at least on the weather side, on global metrics, and we're going to be moving more towards the metrics that, at least my understanding of sort of the weather and climate community is cares more about, like, local errors, extreme events, and also I think we're going to I think we're going to, I think we're going to make progress on the precipitation forecasting problem, and I think we're really close. And then on the models side, I'm very bullish on this. I think that ML is going to appear everywhere. It's going to become part of every climate and weather scientist's toolkit in a really fundamental way. And yeah, that's my vision.
It's hard to follow. I agree with all of that. Yeah, it's wild to look down the exponential of AI, but yeah, 3 years. I hope like so many countries that don't have national high resolution weather forecasts do, because sovereign AI, you can from satellites just train amazing weather forecast models anywhere. That atmospheric scientists will have an updated sense of the predictability limits of the atmosphere as the potential of OBS to OBS end-to-end AI data assimilation unified with AI forecasting becomes realized. Yeah, that like Tian was saying, that we'll have this sort of democratization and transmodality experience where I can talk to my weather forecasts. As a physicist nerd, I would love to talk to today's weather forecast and have it talk in ways I agree about what Rossby wave dynamics are happening to sculpt the current rainfall experience. But I believe all that's totally possible in 3 years, and possibly a lot more that I have no way to anticipate. Or one other thing, and I hope we'll be crushing benchmarks. Like we'll feel like theoretical physicists totally bemused at the fact that our math benchmarks are getting smashed 2 years ahead of schedule by having matured in benchmarking, and with new benchmarks like extreme bench and a lot more.
Thanks. Maybe we can move on online. Ignacio and Francesco. Ignacio, if you had anything to add or any thoughts that you would want to share.
Yeah, so I mean, from my point of view, I think it's an exciting time. So these generative AI technologies and other technologies have already become, I would say, fairly mature to the extent that when researchers are able to frame a problem as in a proper learning way, so as a learning task, usually these methods can actually achieve state-of-the-art performance for many of these tasks. This is a bit more evolved in weather, but I think in climate we're starting to see good progress there as well. And so I'm excited to see in the very near future this technology be transferred to stakeholders of weather and climate information. So I think in weather that's already happening. I think for climate applications we're still not there, but it would be great to see, because that would for sure help us understand, help us validate these methods. I think there were already questions about validation of these methods. So the more users are looking into these methods, the more validation and tests we can do, because these methods behave differently than traditional methods. So it's going to be important to do more validation. And apart from this, I think one more point that I would make that I'm quite excited about is that so far AI models have been used, I think, to like either reduce the computational cost or maybe improve some of the answers that we get from models for weather and climate. But we've tackled this problem similarly as we would tackle them with physics-based models with the same framework. And I think some of the recent progress in generative AI, particularly regarding AI agents that we can interact with, are really going to enable completely new ways of doing climate science. So things that we couldn't do before, because it's just like it wouldn't scale with human interaction. So I can see very easily in just a few years how we can use AI agents to build state-of-the-art models for very niche tasks that nevertheless are important to some users that we would otherwise not be able to do, just because we wouldn't be able to have like a single person working for every specific problem that is of interest for someone. So I think it's going to be a transformative technology for essentially amplifying the value of climate and weather information.
Great point. Francesco, do you want to add anything?
Yeah, I totally agree with the other panelists about the vision in 2 years, and also the difficulty about envisioning something also because of the fast pace of these technologies that are going on. I think that one of the challenges that we really need to face, as Ignacio was also mentioning, is really validation, especially on out of sample distributions. And also considering the shift in distributions of everything that climate change is bringing in our data. So to really trust these models, we will need to really focus on the evaluation on data with distributions different than those that they were trained on, for instance, historical data, especially because in data-driven models like generative models, the only thing that we have are data. And unless we incorporate some physics with equations and something. So we really need to be sure that they can predict something that is different than what they were trained on. And I think that maybe the democratization that machine learning models are bringing in the world, where you actually don't need a supercomputer to run a machine learning model, or at least during the inference, will foster research in this sense even more, and also with the support of this kind of LLMs that are assisting us in a lot of things. But I think that's one of the challenges that we will need to face in the next few years, yeah, at least.
Thanks a lot. I'm going to ask just a last question before we move on to the room, and it's very much what you were starting to discuss in terms of the training, right? So we tend to have now a technology that tends to be a domain. So for our case, climate science or weather forecasting, but then at the same time, you need to know basically the latest innovations in AI, and that's moving so fast, right? So we've been trying to do some of that as part of LEAP, having that curriculum that Tian is leading, the interface between climate science and data science. But how do we avoid the pitfall of jack of all trades but master of none, right, in a sense? So any thoughts on that?
I have the microphone. I guess I'll, yeah, kick it off. You know, I don't work in education. I don't have students. But in my career, I did have a moment when I was working in computational biology, and it was a situation even then that I saw was sort of jack of all trades, master of none, and I didn't want to fall into that, and so I studied computer science. And my sense, honestly, is that it's fine to have collaborative teams where people don't know everything that everybody knows, and I think it's fine to have people who are specialized and to learn other things. So my PhD is in machine learning. I barely knew what a PDE was 4 or 5 years ago, but I fell in love with this field, and I studied and I had a great time. And I had sort of the mathematical background to do it. And if I hadn't had that mathematical background, because I had a hybrid degree of some kind, I would be screwed. So that's my that's my hot take.
Right? You want to?
I think there's a lot of wisdom there. I realize I've been saying for a while in a few settings that I crave bilinguists that have both of this knowledge in their head, enough cutting edge AI, you know, maybe 2 years behind the curve, robust AI, and enough domain science intuition to have really exquisite problem selection. But I also agree that I think training those bilinguists is probably a really long-term process, and it's really important to have depth first on either side of the spectrum, alongside enough core competency and the other side to hang. So yeah, I've certainly benefited at NVIDIA from what you described, deep expertise in different pockets. You know, our researchers collaborate with engineers who have great engineering expertise, and performant machine learning people who know how to scale models, and those are separate concerns. And yeah, there's no way to have all of it inside one mind, but I feel like there is an important Venn diagram as well, a certain set of personnel that are bi or trilinguists that are going to identify really interesting problems that couldn't be identified otherwise.
Thanks.
I've given this a lot of thinking as an educator, and also someone who think about education a lot, given my various administrative roles in the past. I think there's several things. One is AI, like we need to stop thinking AI at the very high level. Like you cannot make any progress if you don't do anything to demystify AI to you. Like AI mean different things to different people, to different discipline. Focus on one or two things that AI is being used in your own discipline would be a very good way of 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 putting a finger on something, right? Otherwise, I just read a paper recently about AI education is like familiarity is a foundation of trust. If you don't feel you know it, you will not be able to trust the technology. And the best way to get to know something that is foreign to you is to start from where you are. So the nice thing is that AI is infiltrating every single discipline. So it's not hard to find at least one or two example where you think that they're doing something, you're impressed by the results, and then dig in. And if it's too intimidating, do it by self. Like grab a friend, grab a teacher, grab a student, and do it together. So that's what I think. What AI education need to do is to have a lot of these like on the ground experimentation and exploration, and then starting from one's discipline. But I also believe that having a very important problem to be the motivation is important. Like everything can be hard and boring and intimidating until one day you run into a problem that you feel passionate about, and that passion will be able to carry you over the threshold. So that has worked a lot in my classrooms.
Yeah, thanks everyone. Definitely a lot has been said that I agree with, and maybe I'll try to kind of summarize it in some ways, right? When we trained, the next generation of scientists or any scientist at any generation, one thing we always tell them is, curiosity will drive you, right? And I think that will remain no matter what, whether it's a specialist or a generalist. But also we tell them you have to be stubborn. So you have to be able to actually hang on to something and want to dig deep. So it's both having the breadth by being curious and having the depth by being able to actually push forward. And whether it's AI, whether it's, whether in climate or something else. So we want to see both aspects. But I think those are the qualities that, we want to continue training scientists with.
Thanks. Ignacio and Francesco, do you want to add anything?
Yeah, I can add something. I think, from maybe a different perspective, I think this is it is a really good problem to have, to essentially have new tools that can make breakthroughs every year. I do think that this essentially enlarges the field. Like essentially, like the number of people working on these problems has substantially, I think, increased because these technologies can be applied to this problem. So we not only see climate scientists and meteorologists working on these problems, but also just pure machine learning engineers, like some of my colleagues. So I think this, in the end, is going to accelerate progress in the field as a whole. At the same time, I don't think that one needs to be an expert in all the frontiers of the knowledge that you can use to advance weather and climate science. And so, an example that comes to mind is for instance, neural GCM, which was recently published, I think last year, and that model is actually using machine learning techniques that are over a decade old, right? They're basically using very simple convolutional neural networks, but they're really combining that with the knowledge of how you can use machine learning to really make an impact in weather prediction and longer timescales. And so I think in the end, knowing some of these techniques and combining that knowledge is going to enable tackling problems from different fronts. And this is going to enable different people with many different backgrounds to actually make progress on this topic. So I think in some ways it might even open up the field to many other people, and it's not going to be it may no longer be a requirement to, for instance, be an expert in geophysical fluid dynamics to make meaningful progress in some of the problems in climate science. So I think it's a good problem to have.
Thanks. Yeah, great point. Francesco, I don't know if you want to add anything.
Yeah, of course I agree with all what has been said by the other panelists. And I was wondering also about an important point that would be instruction and information about the biases that also these models can bring according to the data they are trained on, and also the availability of data across regions, for instance, in climate science. And as a computer engineer working in this field, what I also learned is that the how collaboration and the bringing different expertises all together is really important when working in a certain application domain. And yeah, besides the curiosity of digging into the themes, so without keeping a high level of abstraction, so the different topics that you are working on. So yeah, that's what I wanted to add. Thanks.
Thank you. Okay, we can open up for questions. Yeah, I can give you the mic. Sorry, if you don't mind introducing yourself and where you're coming from. Thank you.
Hi, Emmett Murphy, Nile Point, San Francisco, agricultural food security specialist. I wanted to bring up your point. So you mentioned precipitation, prediction, and democratization. In that, how close are we to real-time precipitation prediction? Thinking about the global south, with most smallholders are rain-fed dependent, and then in terms of affordability of getting that data to very geospecific regions, I'm thinking, throughout the world, particularly with erratic climate, meaning when best to plant seeds in a season because they're becoming increasingly erratic. Like, where are we? How close are we to getting there for that use case?
Yeah, well, maybe we'll let Gideon or someone involved in operational stuff talk about what's available already to consume today. I think there's systems that are already doing AI-based weather forecasting globally that anyone can consume. In terms of your question about crops and planting, I feel like there's a question that's connected to some of the climate interests reflected on this panel. Once you think about crops, you think about predicting growing seasons and growing season length, and that's more than weather. And complex parts of the Earth system become relevant, and ecosystems and soil moisture and maybe even ocean variability have to be predicted on those timescales. And that's still a research frontier that I think the ecosystem is figuring out how to maximize the benefit of AI for. And then ultimately you care about decisions. And so what Tian has mentioned about evolving all of this into agentic systems that can actually be queried. So I think it's going to involve a convergence of some of the threads you've witnessed today. But on the operational part, like, what's live?
Yeah, what is live? Quarter degree global data assimilation forecasts, which I don't think is exactly what you want right now. But if you've been following the work from ECMWF, they are starting to focus on seasonal to sub-seasonal forecasts, which is very exciting. And so this is happening. Talking about the future, we're not doing it yet. We're focused on this archival data set, but I think the promise of our work is to be able to incorporate sort of arbitrarily formatted, arbitrary resolution observations. And so if you have attractive land or you have a specific problem and you have sensors, which I know that a lot of larger agricultural companies do, the hope is to be able to incorporate them for short term, and like I said, there's work being done on the medium to long term.
Sorry if I'm like interjecting here, but yeah. So I've been discussing with quite a few folks, like a couple of examples, like in West Africa or India. So you have a couple of issues. First off is what Francesco was mentioning before, like the quality of the data we use to actually validate, like potentially remote sensing estimates. So for rainfall, that's a major pitfall, and we are really struggling to get there. And in fact, the Gates Foundation is trying to very much focus on that to get better data. So that's a problem right there. I think we have options. We could get cheaper sensors to start mapping that out and getting better estimate, but that's a big issue. The second issue is in terms of what we call the time horizon of predictability. So we've heard a lot of great things about weather forecasting. They make the news every day, so we can have AI-based weather forecast models, but they tend to have very, very weak capacity beyond a few days, right? 5 days. In fact, you can look at videos of those. They tend to be very blurry, so they don't get all of the fine details that you would actually need at a local scale, but they don't really have the capacity to predict very much long term. And that's an issue when we want to think about, say, planting in advance or predicting at what we call the subseasonal to seasonal time scale. So that's a frontier. I mean, we have people here working on that, but that's still a frontier that's beyond whether that's problematic. And then there's a third piece, but we are seeing a lot of action in that space as well, is how do we communicate? So we have a lot of issues. I was in Valencia in Spain last year when there was this major dramatic flood event. Many kids died and people died at the time. And a lot of that was not just the flooding itself, but the time it took to get the communication, the warning in the hands of the people. By the time people were getting the information, it was 8 p.m. We got a notification from the weather forecast at 12. But by the time it was on their phone, it was too late, right? People were actually starting to die. And that's a major gap that we can close, right? There's no reason we have to wait that there should be human decisions at times of action. And so we can potentially bridge that gap, bring in information. And so I was earlier on Monday at an event. So there are people from the Columbia Center in Rio. They are actually working exactly on that type of platform. So an AI-based platform on WhatsApp where people can get the warning message, they can ask questions, and they can interact, looking for safe places to get directions, et cetera, and they can even do it without texting, but also just vocally if they don't know how to read. So that's, I think, a transformative technology.
We have a question over here.
Thank you. I'm Andrew Howley from the Biomimicry Institute. And so we work to learn from how nature works to inspire human innovation and adaptation that's more in harmony with nature and pulls on insights that are going on around us that we just haven't been aware of. So the first thing is a suggestion, which is possibly through in relation to the precipitation models, and wondering how much biological information is pulled into those models, because there's so much that goes on in the tree canopy, in the soil, that's based on biological processes and cycles that might have relevance to refine some variables in there. So I just suggest that. And then the question that I have is something that we've been focusing on, which is making deep science more accessible to people in all sectors so that they can learn from it and apply it. And so we're working on our Ask Nature chat tool, which kind of does that for biology and things that are relevant to how nature's working. But I was wondering, across the board, how much is going on to try to make some of this really incredible data more accessible to people that aren't even thinking that they could process any of it themselves?
That is precisely what motivated the it's a new name which I'm still like AutoClaim DS, which drew on my own experience. I was maybe the newest member of the climate data science community because I came from statistics, and to me, a lot of the terminology and then the data structure was foreign to me. So I can totally relate to it. I just the article on one of my slides was from the climate science community talking about their data access, discover, and retrieval being the bottleneck. So the agentic AI system is that we're trying to, so the knowledge graph we are building take the description of the variables and then recognize that they're actually being named slightly differently from different sources, and then try to, and from their description, we can understand those variable names, what they mean, and then see similarity and cluster them together. So by having this knowledge graph and by working with stakeholders to expand this knowledge graph to capture all this different ways of people referring to things, we're hoping to achieve what you just described. So we're starting, and we believe there are a lot of potential use cases.
That's okay. Yeah, thanks. Excellent point, right? I mean, We all are being trained as scientists. We're trying to communicate, but then of course we're still hitting a barrier where we are producing data or producing knowledge, and we still need to communicate that well beyond, a small audience of experts. So Tian already mentioned some examples. Of course, as it's probably obvious to everyone, putting something on the internet is not enough, right? Because we need to actually attract people to use it and being able to use it. So some of the tools Tian mentioned are one. Second one is we try to actually make the visualization something that people can play with. Meaning you can click on something and you'll create a movie of an AI climate emulator when you can go and click on it, and you will have a time series of temperature and people can move that around. So it becomes also kind of a playful exercise to learn and get a description of what they're seeing and what does that mean. So we're really kind of trying to produce also tools that will be helpful for people to understand what they see, but seeing also how it was generated. So then they actually get the background story behind it. Yeah.
Yeah, I've had two disruptive experiences in the last few years. One was writing this benchmark together with Leap, where we tried to democratize one of our gnarly hybrid climate physics AI problems so that machine learners could work on it. That's the first time someone really confronted me that I speak like a medieval sorcerer. So I think this benchmarking exercise is actually super healthy, and it is the fuel of computer science revolutions. And a big part of that fuel is clear communication, clear APIs. And then I've been really influenced by these product engineers, these kinds of people I've never met in academia who, forgive me, but we have Earth-2 Studio, and there's people that their mission is open source enabling of everyone that's got sub-seasonal models that you could run and download and data sets you can access. And the whole point is usability. And if it's not useful, please give us a Git issue. And if it is, please tell us so we can keep the engineering resources flowing. But yeah, sorry, forgive me for that. Thank you.
Yeah, I love the work that you all have been doing, and I don't know if I guess yeah, my two comments about this maybe A is that automation just goes a really long way, and there's this white paper from someone named David Donahoe about the data science revolution, and it's actually mostly about software and about open source and making things usable, and pandas and other incredibly powerful, but maybe not the most exciting things for us to talk about right here, but have actually revolutionized the field. And yeah, I guess shameless plug, we've tried to make our small contribution to that by making a large observational data set available in that way. So that's the one thing that's sort of like looking into the past for inspiration, and I maybe looking into the future for inspiration. Also, like what Laura was talking about, dashboards and visualizations and all of this stuff. Also, the work that John Tian has been working on. It's going to be compiled from human speech, if that makes sense. And that's just, I think it's super exciting for scientific fields like this because it's going to make things so accessible and quick and intuitive. So I'm really excited for that direction, for that to emerge further.
So the paper Gim mentioned is called Data Science at Singularity, published in Harvard Data Science Review. So if you want that reference. Yeah, also the sorry, it's open access. Yes. So I think should we pin the online?
Yeah,
Yes.
I would just say I agree with what was said. I think that using in particular some of the new large language model capabilities that are coming out and agents are going to enable to democratize the use of climate and weather data.
Yeah, and yeah, just a couple of thoughts. I also think that the way of interacting with the LLMs can be important even in for communication with stakeholders or I mean people outside of the domain, right? Because they allow to interact with the tool to ask questions and solve also any doubts that you have about what you are reading or what's what's there under the hood. And I also think that people are also starting to see some operational some models that are starting to be used in operational settings. For instance, we saw a few days ago the example from Neural GCM that was deployed to help farmers in India to make more informed decisions about when and where to plant their crops during the season according to the predictions of the monsoon for the next season. So I think that these are also, I mean, good things to improve the communication with the public, with the general public.
Great, we have another question over here.
Thank you all for the presentation today. I'm Kira. I'm a second-year PhD student in sustainable development at SIPA. And my question is, so far, I think we all recognize that generative AI can produce some of the really detailed climate projections, but how do you make sure that those models are coherent with the physical reality, not just generating some patterns that look right? Thank you.
I just have appropriate people evaluate them. The same way I think we should defer to like card-carrying experienced meteorological institutions in determining the trustworthiness of AI weather technology. Ever more reasons to be very transparent about training algorithms, open sourcing those and checkpoints so that the whole ecosystem can come to a consensus. But we're not there yet for non-stationary future climate downscaling. That's an open research frontier from my view.
Yeah, I mean, Mike talked about benchmark before, but for this evaluation, right? So we absolutely need to make sure that we get the right answer for the right reason. And that, I can't remember if there was Ignacio or Francesco that brought up, the out of distribution and out of sample issue, right? So we are only training on data that we've seen, but we need to be able to actually, produce projection when we have a shift of distribution, or if we go in a completely out of sample. So really continuing, to rely and develop further evaluation sets and really kind of push the envelope in that sense will be absolutely critical, right? I completely agree.
We have a question back here.
Hi, my name is Joe Wheeler. I'm the CEO of an applied AI company called Blue Movement. And I checked with Molly that this was okay. So if you're an AI engineer, you're a data scientist, it was great to talk to several of you today looking for an internship, or maybe you're graduating. Please, I'll leave my email down here. We'd love to hear from you. My question for the panel is, I had the opportunity, Professor Tim Lenton, who runs the Global Tipping Point conference, I had the chance to come and speak to them. So I was the only software person in a group of 500 climate scientists, which was exciting. I have to say, by the second day, I was ready to throw myself off a cliff. So my question for this illustrious group, and I talked to one of your colleagues, Dr. Gautam John, over at the Global Energy Policy about this on Monday. So I have a question I don't know the answer to, but I'd love to find out, because asset managers, at JP Morgan and BlackRock, they all use the same 4 climate risk products: Aladdin, MSCI, Moody's. There's just a disconnect between what I learned in 3.5 days from these climate scientists and what the value at risk models are informing these asset managers to make choices about risk. So I don't know if it's a question. If one of you can say, Joe, relax, these models are wildly accurate. These managers are making great risk decisions. Though if you agree with me that maybe there's a disconnect there, I'd love to advance that conversation a little bit. I'm not going to miss the opportunity to be at Columbia's engineering school, the smartest people in the world maybe on this topic, and throw that challenge out. And I'd love to hear what you have to say. So thank you for that opportunity. Molly, thank you.
Great question, and I am calling on the panel chair.
I would say relax. Those models are widely inaccurate. I've been actually looking quite a bit into that, interacting with the insurance and reinsurance sector. And a lot of that is also people use the tools that they know, right? And oftentimes you look at those models, they have a lot of deficiencies, but what you have is you have a few providers, they provide relatively similar answer, and that's how people build belief, in those models. It doesn't mean that they provide the truth, but that's how people actually build those tools. It's oftentimes because it's actually easy to use them within the pipeline. They rely on outside providers, and that's really just sometimes also a lack of capacity to innovate in that space. It tends to be different in some other spaces, like if you look at, say, the trading or commodity trading, people tend to be a lot more innovative in terms of the tools they want to use. And because small mistakes can translate into very big numbers, right? So they don't have the buffer potentially that you could have in the insurance sector. So at least that's been my experience. What I'm seeing, though, is that there are needs that they have, especially in terms of geographies or like specific geographies that they might not have, as part of those tools, or specific risks and hazards that they might not have. So, for instance, hail is one that comes back very frequently because that's not part of the standard tools. Flash floods, we hear a lot about flash floods these days. You have dry soils and then you get a lot of rainfall, and that's not really taken very well into account. So that's emerging. And the other one that I'm seeing a lot emerging as well is when people have very, very large portfolios at the global scale, is how do you build some sense of correlation between those, right? You could have a flooding, say, in New York today, let's say, and you could have a drought, say, in California, and they could be connected, right, because of like larger scale synoptic patterns. So those are things that people typically don't consider, but they could have an impact on portfolios. So I think that's emerging.
Just a real quick shout out. So I've got a meeting tomorrow with a large global bank who has some interest in understanding this better. If you'd have some interest in collaborating at some point, I'd love to reach out to you and talk about it.
Yeah, thank you.
I just feel compelled to brag on Pierre and Francesco's behalf about a form of applying generative AI to climate modeling that I think is relevant here, which is trying to distill consensus from and appropriately quantify the uncertainty between different physical models' projections of the future. That itself is a fairly overwhelming analytics task for many practitioners, even those who are deeply familiar with these physics models. And I think that's connective tissue data that generative AI can provide, that Tian spoke to so elegantly about uniting disciplines and data modalities, can also unite these forms of climate simulation that are difficult to sort of distill a consensus from. And Pierre and Francesco have done some really groundbreaking work on this. It was published in PNAS recently.
May we move on? We have a question in the Zoom chat. Validate.
Sorry, can I just add one
sorry,
little thing? We didn't really talk about that, but that came across, that was kind of implicit. And Ignacio, you talked about that, but I think a common theme across was, those generative AI tools, they do great across space, but also across variables, right? And a lot of the risk and the extreme events that we are interested in tends to be what we call compounded. Compounded means that you can have multiple variables at the same time. You could have a dry soil and then like rainfall on top, so that's a flash flood. They could be compounded in space, and they could be compounded in time. And those tools can be great. Even in time, we could have video diffusion. So I think those tools are really, really a very versatile tool to address many of those different challenges. And Ignacio gave that great example. When you use statistical models, typically they do well just on one single variable, and they will miss the correlation between those. Sorry, Catherine. Yeah.
Thanks, Pierre. An online question. Validation of AI output is key to building credibility. For instance, downscaling evaluation is often based on improving the climatology, but evaluations of the changes in the statistics are much rarer. Historically, this has also been true of dynamical downscaling approaches. Can we make sure that these new efforts will be properly evaluated against what we need?
If I may, Ignacio, that might be a good question for you.
Yeah, I can try to tackle it. So I mean, I absolutely agree. I think evaluation and validation of these methods is super important, especially when we're dealing with non-stationary statistics and trying to understand changes, because we don't just want models that that essentially replicate the statistics in the training data. And so, I mean, there's some ways that we can at least validate some of these techniques. So if we think about AI as methods that just can emulate, for instance, dynamical downscaling models, then we already have the ground truth data set, and we can validate against that. And so at Google, we've done some of that work, and we see that if you combine these AI methods with some help with physics-based models, you can actually achieve a generalization to unseen conditions. You basically want to translate an extrapolation problem into more of an interpolation problem for machine learning really to be effective. And of course, if we're trying to move beyond emulation and having systems that are better than dynamical models, then it becomes, of course, much harder to validate this because we don't really have observations of the future. But we can at least check that some of the trends that we've already observed in recent decades can be captured, and so I think as well there for some of the techniques that we've been working on, we see that these methods can capture, for instance, not only changes in statistics, but also the regional modulation of those changes, similarly to what we observe in dynamical downscaling. But of course, there's always a question of whether we're just getting the trends right for maybe a decade or so, and then those trends are going to flatten out. They're not really going to follow maybe the physics that we would expect. And I think that is just an open problem, I think, for machine learning methods in general. And I would say the solution there, beyond validation, which is very important, is just to try to always frame problems that we want to solve with machine learning more of as an interpolation problem than an extrapolation problem. And this can be done, even if we're talking about the future, this can sometimes be done by combining these AI methods with, for instance, physics-based backbones that are telling us about the overall trends of the system.
Thanks. Question? Yeah. If you can introduce yourself, and we're...
Yeah, so I'm Elise Penn. I just finished my PhD at Harvard, and I'm seeing a lot of really promising downscaling of the climate models and the high-resolution weather models, and it seems like this would be really useful for climate risk and extreme weather modeling. And so I'm curious what the barrier is, like what is the remaining barrier to getting those models to be used by industry? Is the technology like just not quite there, or is it more of a problem of it has to be in a format that they can digest?
I can maybe make another comment here. I think one issue when translating these results to maybe the problems that are tackled with industry is that many of the baselines that for instance were referred to before, Moody's and such, those baselines are proprietary. We cannot really take those baselines and compare our models against those. So because they're proprietary, it's really up to the people that have access to them to actually implement our methods and compare them. But from our side, there's always going to be that disconnect that we cannot really compare because many of these baselines that are used right now for climate risk are not open source. So that's just my perspective.
I think the world desperately needs a benchmark in this category to help us disambiguate the progress and challenges. To me, the obvious benchmark that has like a gold standard of like approval in the community is dynamical downscaling done well. Someone alluded to all the issues of doing it well, but there, if folks can encapsulate that in a benchmark, the challenge is that not all regions of the planet have been dynamically downscaled from not all plausible versions of the future spanning CMIP models. And so that's a fundamental compute constraint, actually, is that it's too expensive to do that. This is where I'm really excited about things like Stormcast. If we can prove that AI can replace autoregressive models on the convection resolving scale, then we sidestep the computational barrier to doing dynamical downscaling in a way that could generalize the way that autoregressive physics models can sometimes generalize. So yeah, I think these are reasons to benchmark, to distill the wisdom of the dynamical downscaling community in a way that people can really unambiguously say yes or no, we're ready to do that.
Okay. My name is Jason Han from Biomedical Engineering Department at Columbia. That's me why I'm here. Very cool talks. So obviously we were talking about climate science, but as I'm listening, it seems like we're getting better and better at predicting weather, climate. What's the kind of prospect of going beyond climate engineering? I want to kind of hear about kind of your vision towards that? And kind of related to that, when do you think, my understanding is that generative AI and the cycle technology super expensive to begin with. What's the kind of path towards making it fill that deficit from here on, specifically in climate science or climate in general in this earth, and then trying to make it beneficial?
Yeah, if you can run an LLM on your laptop, you can run any of these models. So full stop. I hope that is satisfying. Sorry, what was your first question again?
Oh, kind of path towards like climate engineering.
Oh yeah, well yeah. I mean, there was sort of a trend in machine learning maybe 5 to 8 years ago on causal machine learning, and I think that would be the direction to take this to answer questions like that. And it's, in my humble opinion, very underdeveloped. And it's sort of the interesting thing about that from the climate perspective is causal physics, long-term rollouts, they all kind of amount to the same thing. And that's having a physical, mechanistic understanding of the system. And this is, I just think, the cutting edge of research. Some people are really pessimistic about this, and we will never get there. And we're only emulating. And as soon as we go out of distribution, we're going to tank. And I just think we don't know. Maybe the optimistic view is there's someone at NYU named Andrew Gordon Wilson. He came out with a single author paper recently, sort of in theoretical machine learning, about using other theory to analyze machine learning models other than the normal sort of statistical risk minimization framework. And I'm not a big expert on this, but seemingly, long story short, is maybe these models are actually learning programs. And if they're actually learning programs, well, equations are great, but what we're actually using are programs. So maybe we actually can get there, if that makes sense.
Great. Maybe we'll take a quick last questions and then we'll
We have one
close.
last question back here.
Sorry.
Hi, this is Gabriel Carino from Columbia University, LEAP. You guys talked about, you guys talked about the importance of validation and, but also people struggle in tracking the progress of these AI-based emulator, AI-based products, right? So the way we have to track this progress is through benchmark datasets, right? And in general, benchmark solution. So my question is a GenAI posing new challenges and also new features that we should take into account in developing the next generation of a benchmark dataset and solutions? Thank you.
Yeah, great question. Definitely, actually being able to track progress to begin with has been very difficult because there are so many models across the board that are actually targeting different, aspects of the problem. So I don't know if it raises new challenges, but I think definitely helps us ask more questions. So, kind of moving forward, being actually more thorough. And I think one of the questions online was, kind of exploring statistics, right? And exploring extremes. Now, of course, you're faced with the fact that you don't have enough data quite often to compare against. So I think that might be one of the big challenge, right, that we continue facing, making sure that we actually have enough data to compare, those new model with. But I think at the end of the day, it becomes something of a community. So Mike talked about, ClimSim, this kind of benchmark developed within, within LEAP. But now it's also for the community to continue develop and push forward this next generation of benchmark for us to really kind of be able to not just track progress, but to see where the challenges remain. That can also open, new opportunities of what are the missing data sets, right, to actually be able to answer some of the key questions. So it's a, back and forth kind of problem.
And I heard in the question also some interest about like particular challenges of Gen AI when trying to benchmark. I feel like one of the common ones is the apparent expense of it. I really want to emphasize that folks in industry that are doing image and video generation for real products where inference is dollars, have developed all kinds of tricks to beat down the inference expense of diffusion models once trained. And please contact me if you could use some references there. But the other unique challenge of generative models is because they're conditionable, which makes them so powerful and interesting, it's possible to condition them naively. And there's a very large degree of freedoms of how one might get into trouble doing that. So I would just emphasize the importance of consulting with domain scientists about the causal relevance of what you're tempted to condition them on before benchmarking. Thanks.
I want to address the second part of the question about generative AI enter the arena and what kind of like issues and concerns. Generative AI it's a generative, right? Like it's a probability like a generation of the next token in a sense, right? So everyone who have done anything with ChatGPT know that they always sound so confident because they always give you one version of the answer and you know there are multiple possibilities. So I think to me as a statistician, the next important direction of research is how to do an uncertainty quantification correctly. And uncertainty quantification is not just about estimating the amount of uncertainty, is to actually delineate in uncertainty in different scenarios in the sense that what, producing uncertainty estimate to be contextualized, within the question that need answer, because some uncertainty may be large for one question, but may actually be irrelevant for another question. And currently they're all mixed in one pot. Like you look at the uncertainty of the climate model, it look pretty bad. But then if you look at one particular direction, that can actually be rather reliable. And to find where things can be reliably used and where things that still need further data for the model development to be refined is a ongoing effort, at least from my perspective.
Great. So we'll close on those great words. And thanks to the panelists and thanks to for joining us today.